Hello everyone, my name is Ziwei from the University of Hong Kong, and today I want to share something about turbulence scale analysis in roughness sublayer and inertial sublayer of real urban morphology. First, it's about the background, because in our traditional method we use log law to describe wind profile, but in fact the log law in roughness sublayer is not applicable. Uh, and in roughness sublayer, there also turbulence inhomogeneity existed. So in this work, we want to figure out the reason why the log law is not applicable in roughness sublayer from the turbulence scale point of view, and the scale interaction uh, uh, of the turbulence. And in our experiment, we also find the dispersive stress in roughness sublayer is relatively large than other region. So it means in this area, there exists a large inhomogeneity. Uh, um, this is about our methodology. First is the Guangdong experiment. We select Guangdong Peninsula in Hong Kong Island, and for the model we use 3D printing, and the ratio is 1/1200. For the Guangdong experiment, we select three planes, first and second, third plane. For each plane, there exists um, 46 wind profile, and for each wind profile, there are 96 sampling points. And then we use the Chun-Ho analysis to investigate the turbulence motion scale, because we know that Q2 and Q4 sweep and ejection dominate the turbulence in roughness sublayer. So in this part, we calculate the momentum transport efficiency for each quadrant, and then we use empirical mode decomposition of a velocity signal. This is the main steps of this method. First, identify a local extremer of the variable xt and interpolate between all the minima to obtain the signal envelope and get the maximum and minimum envelope, and then calculate the local mean. Then subtract the local mean from the uh, original velocity signal and get local detail. And finally, we calculate the intrinsic mode function. After all the procedures finished, we will get several intrinsic mode function and one residue. First, we use a low pass filter for our velocity signal. Uh, for low pass filter, we change the increasing cutoff frequency and get the momentum flux for each cutoff frequency, and then calculate the momentum flux contribution from every cutoff frequency. And this figure shows the momentum contribution at different turbulence scale. From this first plane, second plane, and third plane. Uh, from this figure, we can see that with the turbulence scale decreases, the momentum contribution increases, and And in this region, for the first plane, because there is a high-rise building here, so the momentum contribution in this area is less negative. But for the second and third plane, there exists a positive region. It means in this area, uh, there the large scale turbulence influence the momentum transport here. So this is maybe the reason why the log law not applicable in this region from the turbulence scale point of view. And then we calculate the motion scale. Uh, in, in, in this part, we get the motion scale for every quadrant. Because the Q2 and Q4 sweep and ejection dominate the momentum transport in roughness sublayer. So we mainly talk about Q2 and Q4. Uh, from this figure, we can see that uh, the Q2 and the momentum transport efficiency is larger in Q4 in RSL. It means the Q4 dominant the momentum transport, and the motion scale for Q2 in RSL can be up to 5 to 6, but for the Q4, the motion scale can be up to 10 to 12, and with the height increasing, the momentum transport efficiency increases for Q2. And also we calculated the exuberance EXH. For this part, we use the EXH to quantify the momentum transport efficiency. First, we got uh, the ratio of each quadrant event, and then calculate the exuberance by the uh, SEH plus S3H over S2 plus S4. So it means when the EXH close to zero, the momentum transport efficiency is larger. And from this figure, we can see with the whole set increasing, the momentum transport efficiency increases, and also uh, the uh, the largest momentum transport efficiency appears in ISL in the solid line and dash line in this area. And because of the high-rise building of first plane, in this region there is a large negative region. And for the second and third plane, the conclusion is same. And the largest momentum transport efficiency appears in inertial sublayer. And then it's about the EMD. From the empirical mode decomposition, we got several intrinsic mode function and and residual. For each mode, we use FFT to got the characteristic frequency. From this three figure, we can see that for each mode, we can get a characteristic frequency, and all the peak value from the line following minus minus factor law, and uh, and the energy from large scale to small scale increase first and then decreases. And for the pre-multiplied spectra, we can identify the length scale for each plane. From the first plane, for the first plane, uh, the largest turbulence scale uh, is smaller than the other two, and for all the three planes, uh, the turbulence length scale is roughly equal to 200 millimeter and comparable to the boundary layer. It suggests the momentum entrainment is from the boundary layer. And then we calculate the amplitude modulation to find the relationship between small scale and large scale. The main procedure is to calculate the large scale and the envelope of small scale and get the correlation coefficient. And we we had the three plane result. In the RSL, there is a positive relationship between the large scale and the small scale. And in the inner sublayer, uh, the relationship is positive. It means in the RSL, uh, the large scale turbulence accelerates the small scale turbulence. But in ISL, uh, the large scale turbulence deprives the small scale turbulence. And this is the main conclusion. For the first part, we got the momentum contribution for each quadrant, and with the whole size increasing, the momentum transport efficiency increases. And for the low pass filter part, we use this method to quantify the momentum contribution at different turbulence field, and we can find that the positive momentum flux appears in the low region RSL. And for the EMD, we can get the characteristic turbulence length field for each move. Yeah. Thanks for your I think we have time for one question.
First of all, thanks to use my PhD thesis picture in your first page. I saw you use a picture. It's from my PhD thesis. Okay, so thanks. And the second one is you are just stressing you are analyze the amplitude modulation, right?
Yeah.
I think maybe you can reference the paper from Lohan, Bailey, and Homan Matisse and Blackman Karin.
Yeah.
They are working on this kind of area and do a lot of work in physics matter. Okay, my question is how what the momentum flux you are mentioning, just the turbulent momentum flux or dispersive momentum flux. How can you celebrate each other and can you give me a hint? Thanks.
The turbulent the momentum flux I mentioned is just the turbulence momentum flux, not dispersive flux. I only use the dispersive stress in my first paragraph to evaluate the spatial variation in roughness sublayer. But the following momentum flux I mentioned is just the turbulence flux. Any questions?
I just thank you for the presentation. First, question about the Guangdong experiment. You show us really briefly. I'm not sure about the boundaries. You show us in the video.
The bottom button is the back button.
The back one.
The bottom one is back.
Okay. This one.
Okay, so Yeah, actually, the walls are very still highlighted in the figure. The light stripe. You have the what is the region of your wind tunnel position? It's measured in the wind tunnel. That's right. Yeah, yeah. So, what are the lateral boundaries of your model?
Boundary layer is around 180 millimeter.
Boundary conditions. Boundary,
boundary
the walls of your wind tunnel on the lateral sides.
Boundary condition is a constant velocity.
No, I mean the width.
With
With
You put your model just
6 meter long wind tunnel and 550 millimeter wide and
half a meter wide.
yeah,
And
and
you put the model of Urban just to the walls of the wind tunnel.
yeah.
So I think in this case you have really reinforced and overestimated the vertical momentum on your wind tunnel. So I maybe next time recommend to more wider like a single one because you have the force of flow in one direction. So maybe some results are overestimated.
And because we select plane is made of the wind tunnel, I think the influence is not solar.
Maybe do it for smaller area, but also consider the lateral boundaries.
Yeah.
Thank you.